Well, this is our final lecture. We will start off and discuss phase velocity, group velocity, energy velocity, and these are all defined differently, and I think they tend to be a little bit mysterious. So hopefully we can bring some clarity to that, because we have to have a firm understanding of those and the differences between them before we can discuss what slow waves are and how to generate them. Given that, then we'll start discussing structures and configurations that produce slow waves, and I have those roughly divided into two categories. There's resonant structures that produce slow waves, like photonic crystals, things like that, and then also the pure bulk materials that can also produce slow waves. On to the phase, group, and energy velocity stuff. First, what is phase velocity? Phase, we're looking at the actual wave itself. So imagine throwing a rock into water and you watch the ripples propagate. If you trace your finger along those ripples and you look at how fast your finger is moving or how fast that ripple is moving, that is phase velocity. And we actually define phase velocity as the frequency, that's the angular frequency, radians per second, divided by the wave vector. So this is 2 pi over the wavelength in the medium. And so this is how we define phase velocity. It's the velocity of the actual wave itself. Your fingers tracing the hump of the wave. And so the animation here is just showing a wave going from left to right. And if we trace the speed of the red vertical lines, for example, and we look at how fast that's going, that's phase velocity. Here's a quick derivation of phase velocity that we'll use again when we get to group velocity. We start with a general expression for a wave. So we have a sine of a kx minus omega t. Now, the trick here is the wave moves at a speed that makes this argument a constant. So we'll choose 0 for convenience. So we'll take the argument of the sine and set it equal to 0. Then we're going to rearrange some terms. We'll bring the omega t over to the right-hand side, so we have a kx equals omega t. Then, if we bring the t over to the left-hand side and the k over to the right-hand side, we get this ratio. But notice we have a distance term, or a length term x, over a time term. So we have something that's distance over time, or meters per second, something like that. That's a velocity. So it turns out the omega over k is a velocity. And since we derive this from the phase of the wave, the argument of the sine is an angle, it's a phase, we derived it from that, we call that a phase velocity, and it is omega over k. Well, given that there's a velocity of a wave that could potentially be slower than the speed of light, it makes sense then that we can extract some kind of refractive index from that. So the refractive index that we extract from phase velocity, we'll call the phase refractive index. So we'll put a subscript of a p here to indicate this is the phase refractive index. So if the wave is traveling slower than the speed of light, the velocity in that medium will take the speed of light and divide by some constant. That constant is the phase refractive index. So if the phase refractive index is 2, then the phase velocity is half the speed of light. Now it turns out that inside a waveguide, that the phase velocity can approach infinity. We can think of the mode inside a waveguide as the interference between two plane waves. And I'm showing these up top here. We have one plane wave that seems to be angled a little bit down, and another plane wave that's angled a little bit up. And we can trace our fingers along these vertical red lines again, and we can see the phase velocity. Or we can look at the interference between these two waves, and we see something that looks like a guided mode, and we can trace our finger along the red line again, and we'll have the phase velocity of this mode inside the waveguide. Now in this configuration, it doesn't appear anything magical happens. But let's go to a higher order mode so that these waves inside the waveguide, the two component waves, are at a steeper angle. Play the movie. And what we see now, we have a very, very high order mode. And again, we can trace our finger along this red line, and we can see phase velocity of the component wave, if you will, and here's the other component plane wave traveling upward. But if we look at the interference between these two, and we trace our finger along the mode, what we see is this mode is traveling very, very quickly. And in fact, if we go to a really high order mode, the steeper the angle that these component plane waves are propagating, the faster this phase velocity inside the waveguide. And in fact, the phase velocity can approach infinity simply as those two component plane waves approach being vertical. So we can ask ourselves, does anything actually travel faster than the speed of light? Well, we're just looking at the interference between two rather ordinary waves that are propagating at rather ordinary speeds. But if we look at the interference of those two, that interference pattern definitely can travel faster than the speed of light. So is anything actually traveling faster than the speed of light? Can we do anything with that? Well, probably not. The next topic is group velocity. And when we talk about group velocity, we're talking about something that's no longer a pure sine wave. We're talking about a spectrum of frequencies. And there's certainly the potential here that each frequency can travel at a slightly different speed. And if we get this bandwidth due to some group of frequencies, if you will, or a signal, that could potentially travel at a different speed than any one of those pure sine waves by themselves. So we're really looking at sort of an envelope effect. How fast does the envelope travel? So in this animation, what we see, if we were to put our finger on the red lines, the vertical red lines, and trace them, they're moving very quickly. Phase velocity here is pretty fast. Yet if we look at this overall envelope of the waves, that's traveling much more slowly. So group velocity can be slower, much slower than the phase velocity. How do we define group velocity? It's actually the derivative of our frequency with respect to k. Now, at this point, that probably does not make much sense of why we have that definition. So we're going to get into the derivation of that, and hopefully it makes a little bit more sense. Just like phase velocity, if the wave is traveling slower than the speed of light, it's useful to come up with a constant that describes a factor by which it slows down. If we extract that from the group velocity, we'll end up with what we call the group refractive index. And it's just a factor of how much the wave slows down. Here's our group velocity. Over here's speed of light. And the group refractive index is that factor by which the wave slows down. So if group refractive index is 3, then the group velocity is 1/3 that of the speed of light in outer space. Here's another, probably a little bit more classical animation of phase velocity versus group velocity. And what we see at the bottom, if we trace the humps of the waves, so we'll trace this hump here, that's phase velocity, and that seems to be traveling rather fast. Yet, if we look at the envelope, we're placing a green dot here at the minimums, and if we trace the movement of the green dots, that is moving much more slowly. Here's a red dot tracing the actual wave, that's phase velocity. Phase velocity here seems to be faster than group velocity. Group velocity tracking the envelope of that wave. So these can be different, and when we derive it and look at the equations, we can actually figure out what are the conditions where these will be different. So I mentioned before, group velocity is really when we have a group of frequencies propagating together and we need to track the envelope. So rather than look at a whole spectrum, let's just look at two frequencies. So we have an electric field that is the sum of two waves at different frequencies. So we have a K1 and a K2, also an omega 1 and an omega 2. We have both of these waves added together and traveling at potentially different speeds. If their K vectors are different, the omegas are different, they may have different phase velocities, but what does the group of the two waves do? So remember the trig identity. If we have the sum of two sine waves, we get a sine times a cosine with sum and difference frequencies. Well, our electric field was the sum of two sine waves, so we can apply this trig identity, and now we have a sine and cosine of sum and difference frequencies. That's sort of the first step in our derivation. I'm going to write that last equation on the previous slide slightly differently. We still have the same sine and cosine, but I'm grouping some terms together. And what we have inside this original sine is a average k vector, if you will, or a center k vector, a center frequency, which makes a little bit more sense. Then in the cosine term, where we have the differences of omegas and k's, we actually have the delta k, the difference in k's, minus the difference in frequency. So this can really help us track our center frequency and our bandwidth and see what happens. So what does this look like? Well, this term, the sine wave, is fast. We have a center frequency which is probably very high. So that sine is what's responsible for these very fast oscillations. Then we have this term, and the delta k and delta omega are probably much smaller numbers. This is responsible for an envelope. And so that cosine is this cosine envelope. So when we add two sines together that are slightly different frequencies, we get something that looks like this, where we have this rapidly varying sine wave inside this envelope. And our trig identity led us to a form that shows that more clearly. So at this point, we have identified this cosine term that contains the delta k and the delta omega as the envelope term. So the question is, how quickly does this envelope move? This is the this is the information on the wave. How quickly does that move? Just like what we did for phase velocity, this moves at a velocity that keeps the argument a constant. So let's choose 0, and on the next slide we'll see what happens. Okay, so we start with the expression from the previous slide that we're going to set equal to 0. Then we differentiate that equation, and we end up here. And so the change is our x goes to a dx and our t goes to a dt. Now, we take this expression and rearrange terms just like what we did for phase velocity. So we'll bring this delta omega dt term over to the right-hand side. Then we'll bring the dt term over to the left in the denominator, the delta k term over to the right in the denominator. And here we are. And we have something now that again has units of distance over time, or velocity. So our velocity in this case is a dx dt, that's obvious, but also our delta omega over delta k. So this is almost group velocity, not quite. Group velocity is this delta omega over delta k. However, we're going to take the limit as our delta omega and delta k goes to 0, in which case our delta omega delta k ends up being a d omega over dk. So the derivative of omega in k space, if you will, or the derivative of frequency with respect to the wave number, that gives us our group velocity, the speed that that envelope moves. Not the speed of any of the individual waves, but the envelope. So this was a one-dimensional case, and it turns out the three-dimensional version of a derivative is a gradient. So our group velocity, which is a vector quantity, is the gradient of omega in k space. And if you haven't taken the computational electromagnetics class, this probably does not make much sense, but this is the omega that we would calculate from something like the plane wave expansion method. You give it a k vector or a block wave vector, and you get back a bunch of omegas. And if we take those bands and we differentiate them, we get the group velocity. Let's look quickly at what happens with ordinary materials. We'll start on the upper left with the dispersion relation for an ordinary material. This may look a little bit different than what we've seen in the past simply because rather than having k squared on one of the sides, we had a kx squared plus ky squared plus kz squared. But we don't need the components in this case, we can just go with the magnitude squared. So this is the dispersion relation for a nice, well-behaved ordinary material. We'll rearrange the terms a little bit. We'll take the square root of the equation, we'll bring n and c over to the right-hand side, and we end up with this equation. So really, we have an equation that is omega in k space, or omega as a function of k, for an ordinary material. We know we have phase velocity defined this way. So in fact, the c0 over n is our phase velocity. Let's take this equation and calculate the group velocity. The group velocity is essentially the derivative of that equation with respect to k, and when we take that derivative, we just end up with c naught over n. So in other words, for this ordinary material, the phase velocity and group velocity are exactly the same thing. So when on Earth could they be different? Let's add dispersion. So this is our original dispersion relation. We will differentiate that because now if we have dispersion, the refractive index is a function of frequency. So now we can differentiate it, and n is no longer a constant. So when we differentiate the equation with respect to frequency, we get an omega dn plus n d omega equals c naught dk. Now let's rearrange these terms, and here we are. And what we see is over on the left-hand side, we've grouped terms, which is our phase velocity. And on the right-hand side, we saw a d omega dk. That's our group velocity. Now we have an equation relating the two, group velocity and phase velocity. That'll give us clues of when these terms will be different and when they'll be the same. So let's do those substitutions. On the left we had phase velocity, on the right we had group velocity. An easier way, I think, to figure out when these are different, we'll solve this for group velocity. So we have group velocity equals phase velocity minus this group of terms. So clearly, when this group of terms is 0, that's when we have the phase velocity equal to the group velocity. Well, frequency and refractive index are never equal to 0, or refractive index is never really infinity. So it's this derivative term. So in other words, if refractive index is a constant with respect to k, or in other words, refractive index is just a constant, it doesn't change, there's no dispersion, then phase velocity and group velocity are the same. It's only when refractive index is changing, that whatever material this is, it's dispersive, that suddenly group velocity is now smaller than phase velocity, potentially smaller. It really depends on the sign of this derivative. So, based on those previous equations, we can now derive expressions for our phase refractive index and our group refractive index. Here's an expression for our phase refractive index, and then an equivalent expression for our our group refractive index. And the way we've written this is we put the group refractive index also in terms of the phase refractive index, so we've related those two. And again, these will be the same, the group refractive index and phase refractive index, when this term, or this term up here, is 0. And we may like it in terms of omega, or may like it in terms of lambda. Either way, when these terms are 0, again, refractive index does not change. Group and phase velocity are the same. Group and phase refractive index are also the same. So it's dispersion in the lattice, the material properties changing with respect to frequency or wavelength, that lets group velocity be different than phase velocity. So here's a summary of the whole phase, group, and energy velocity. I know we saw this before. So phase velocity is defined as omega over k, and we can derive a phase refractive index from that. Group velocity is the gradient of omega in k space. When there is no dispersion, group and phase velocity are the same. We can also define something called an energy velocity. And in linear materials, these two are the same. But inside nonlinear materials, it turns out the energy can travel at a different speed than the information, or the group velocity, and the information can travel at a different speed than velocity. So they can all be different. But we need dispersion, and we need nonlinear materials in order for these things to be different. And so I'll also repeat this that we talked about with index ellipsoids. We can draw our isofrequency contour, or our index ellipsoid. Phase travels in a direction that connects the origin to some point on the surface. So that's our k vector, and that's the direction that phase would appear to be traveling, or that's the phase velocity sort of direction. The direction of the information is normal to this surface. And so the group velocity travels off in this direction. Now when our index ellipsoid is a circle, our phase velocity and group velocity are the same, but Now that we don't have that, we have an ellipsoid, they can be different. And in something that's anisotropic, that would give you that, the refractive index does change with things. If we change direction in the lattice, it changes. So again, it's dispersion that leads those to be different. And we've also seen how in photonic crystals that phase and group velocity can be in different directions due to the dispersion induced by the photonic crystal. Finally, on to slow waves. So, what is a slow wave? We define slow waves in terms of the group velocity, not the phase velocity. And we already know now that there's this relationship between group and phase velocity where the group velocity can be different. It can be slower or it could actually be faster, depending on the sign of that derivative term that quantified the dispersion. So, because we say this dispersion causing slow waves, really this phenomenon is happening because whatever material or medium this wave is traveling through, there's somehow this increased interaction with the material, and that is what is slowing down the wave. So if we're in outer space, we can't have slow waves. We have to be traveling through some kind of material or medium. Can't do it in outer space. So how do we slow the wave? Let's go back to where we related group velocity to phase velocity, and we will generalize this to 3 dimensions. So where we had this derivative of n with respect to k, we'll put a gradient in here. So here's the general relation between phase and group velocity. And likewise, we can relate the group and phase refractive indices. So in other words, we have to induce dispersion to get slow waves. So there's 2 broad ways that we can induce dispersion. We can somehow find materials that are dispersive, or we could cause the dispersions ourselves with gratings and photonic crystals and things like that. So these are the 2 broad categories that we'll study slow waves, and we'll look at mechanisms in both categories that can cause slow waves. But in any case, somehow the material that the wave is traveling through is dispersive. The refractive index is changing, and that's the mechanism that slows the wave. So we know generally now how to slow down a wave. We introduce dispersion. Let's ask the question, is it possible, or how can we stop a wave? Well, let's look at that expression for the group refractive index. Remember, the group refractive index is the factor by which the wave slows down. Well, if we stop it, this has to be infinity. So this term, d omega, has to somehow be positive or negative infinity. So if we take the reciprocal of that, 1 over dn omega, that has to be 0. In other words, if we look at our dispersion, we plot refractive index versus frequency, we'll see regions where refractive index is flat. There would be no slow wave, no dispersion here. If this had an infinite slope, we could stop a wave over this very narrow band of frequencies, or if it's an infinite slope, it really would just be at one single frequency. So yes, in principle, we can stop a wave if it's a pure frequency and our dispersion has infinite slope at that frequency. So we mentioned before, there's 2 broad categories for slowing waves. We can choose materials who, at the atomic scale, is somehow producing the dispersion that we want. So I'll call that material dispersion-based slow wave devices. And then there's also the structural dispersion, photonic crystals, waveguides, Bragg gratings, coupled resonators, that sort of thing. Now, it's the second category, structural dispersion. These tend to be the preferred or most studied, simply because they're rather easy. Everything else requires something usually pretty extreme, like cryogenic temperatures or something like that. So we tend to see more of the structural dispersion type of approaches. Not to say that there isn't anything to the material dispersion. I think there's great things there. We just tend to see more on the structural dispersion because it's easier to do. All kinds of applications that we can slow down a wave. We can reduce noise in systems. We can switch signals. We can buffer signals. In other words, store them temporarily because we can slow it down. Some really cool time domain signal processing that we can do by slowing waves down. We can resynchronize clocks. If clocks get out of sync, we can slow one down. All kinds of different ways for controlling information in the network. We can do pulse compression. We can make interferometers more sensitive because if we slow the wave down, the wave is traveling effectively longer, making our interference much, much more sensitive. We can miniaturize. If we can slow a wave, we reduce the wavelength. And if we reduce the wavelength, we're reducing the size structures it takes to manipulate that wavelength. We can use this to enhance linear and nonlinear effects. Because the wave's traveling slower, it's interacting with the material more, it has to enhance all those different effects. And there's applications for this in particle acceleration. And this is probably just the tip of the iceberg. I think there's a lot of applications for slow waves that I'm not even touching here. So when we discuss slow waves, we need to talk about some metrics of their performance. Now, the two obvious ones, we would probably like a slow wave over a wide bandwidth. And then we also have the dispersion or the delay. How much do we slow it down? And we probably want both of these large, but what we'll see is that there's a trade-off. And we can see that real clearly through the dispersion curve. Let's take a dispersion curve that has a really steep slope. That means we'll have a lot of dispersion. The wave will travel much more slowly. However, that means it will probably have a small bandwidth, simply because this curve is jumping so high. We would, in order to extend the bandwidth, it would have to jump to a higher and higher and higher and higher refractive index to the point where it really gets unreasonable. Whereas, if we can get away with less slope, we have smaller dispersion, but we can do this over a much larger bandwidth. So what we see right away, there's a fundamental trade-off between bandwidth and how much we can slow the wave. And these two pictures, I think, illustrate that as clearly as I can conjure up. So a single metric that can quantify all of this is what's called the delay bandwidth product. We want delay large, we want bandwidth large. So when we multiply the two, this delay bandwidth product is something that we want large. So it's the delay that you would get in a signal over the bandwidth, times the bandwidth. And it turns out we can express it this way: the length of the device times the change of refractive index over the operating bandwidth divided by the wavelength. Now very often, let me back up a little bit, it's obvious if we have some slow wave device that gives us some delay, if we double the length, that'll give us twice the delay. That's pretty obvious, so it makes sense then to normalize this by somehow removing the length term, because we know we can always make it longer to introduce more delay. So very often we use what's called the normalized delay bandwidth product, and I think that's the more useful quantity, because we know obviously, yeah, we can make it longer to induce more delay. So, in fact, the normalized delay bandwidth product is defined this way. And it basically comes out to this delta n parameter, the change in refractive index over our operating bandwidth. So on to our first class of structures that can produce slow waves. That's the resonant type. So these are the photonic crystals, the Bragg gratings, these types of things. Perhaps the first ever slow light device is just a standard rib waveguide. We already know from previous lectures that crazy things happen near cutoff. And near the cutoff of a waveguide, they get very dispersive. And in fact, we can just operate near the cutoff of a waveguide to introduce the dispersion that would slow our wave down. And in fact, we can do that, and that happens. We can enhance that with something like a photonic crystal waveguide, where there's an additional interaction mechanism because of the photonic crystal. We can slow things down even more. So photonic crystal waveguides are actually quite common slow wave devices. Slow light, we would even call it. It turns out that the group velocity can also change as a function of frequency, and very often we want to control that in some way. Maybe we want to make it constant, or at least a linear slope. So the way this is done then is we take our slow wave device and we chirp it. So it essentially affects each frequency in a different portion of that slow wave device, if you will. And we can flatten the group velocity dispersion. We can do other things. We have a device that's called a coupled photonic crystal waveguide. So let's look at what's happening here. We have an input waveguide, and we already know that can be somewhat of a slow wave device. Well, here it splits into two waveguides that are close enough to be coupled. And in fact, we're engineering the coupling here with the photonic crystal. So there's a lot happening here. Not only could we operate near the cutoff of a waveguide, there's the interaction of the photonic crystal plus the coupling between the waveguides. So there's a lot happening here. There's a lot of interaction of the wave and the device that gives us dispersion and gives us slowing. And then finally we have our output waveguide. So macroscopically, this is just a huge delay. This might look like it's a mile long. So we can introduce a lot of delay and dispersion by introducing more interaction of the wave with whatever it's in. Here's a device that claims zero dispersion for slow waves. And what you notice is that we're chirping the hole size here. We have our waveguide surrounded by a photonic crystal. And it's maybe hard to see, but notice that the hole size increases as we go outward. And if we look at the group index versus frequency, what we can see is that it's a rather straight line in this region of being a slow wave. See a nice straight line over here. Again, here we have less dispersion, but over a wider bandwidth. And here we have more dispersion over a narrower bandwidth. So we see our typical trade-off, but we also see that this is rather flattened. And by just engineering this taper, we can make those flatter or less flat. Another whole approach to do slow waves is something called coupled resonator optical waveguides, or CROWs. And so imagine we pump light into one of these waveguides, and now it excites this little ring resonator, so photons start doing circles here. However, it's coupled to the next ring resonator, and photons start doing circles here, and that's coupled to the next ring resonator. And so clearly there's going to be a whole lot of interaction with the electromagnetic wave and this configuration. And so we can do a lot of tuning. And in fact, there's been a lot of research in these coupled ring resonators to slow light and do other things. There are a lot of folks looking at anisotropic materials to stop light or slow waves down. And in fact, nature only gives us so much in terms of anisotropy. In fact, we talked about this when we talked about anisotropic metamaterials. So metamaterials comes in, and that lets us do even stronger anisotropy. So this plays a role in these slow wave devices because now we can use stronger anisotropy to slow waves down even more than we could with just naturally occurring anisotropic metamaterials or anisotropic materials. So in one case we can slow light or slow a wave by having some kind of core, and here just air, and then surrounding it by two anisotropic metamaterials. And we have a guided mode in here, and it would slow down just due to the interaction with the anisotropy, which is kind of neat. And then here's another type of structure that folks have used to try to stop light, and there's a little waveguide cavity, if you will, that just gets pinched down. But you'll notice on either side of this guide is an anisotropic metamaterial, this layered structure. And in principle, this could stop light. Now, if we combine some of what we know from photonic crystals, where we have band diagrams and stop bands, with anisotropy, we can do some neat things to slow down waves using something called a degenerate band edge. So let's look here. We have a photonic crystal. So we have layers going in the direction the wave is traveling. It's a photonic crystal, meaning the wave is bouncing back and forth in these layers. But we also see that they are a sub-wavelength grating, so they have artificial anisotropy, if you will, and the anisotropy is at different orientations. And here's an actual device realized by Dr. Fitty. And so a wave would be launched in this direction and would slow down. So it's a photonic crystal in the z direction, so we can plot bands. And it turns out there's three flavors of these bands. There's the regular band edge, and we notice that the slope does tend to flatten near the band edge, so there is some slow wave behavior at the band edge. Remember, group velocity is the derivative of omega in k space, so we have our frequency, our omega axis, and we have our k axis, so we are looking for flatness here, but the regular band edge only does so much. Then we have something called a split band edge. We notice that there's two of them. It's splitting, and we might see a little bit more flatness here, not sure. But then we have something called a degenerate band edge. Look at how flat that is. So over this narrow range of frequencies, somewhere in this case around maybe 1.24, we get very, very, very slow waves due to the degenerate band edge. Now, what the word degenerate means, we haven't used that yet in this course, but let's suppose we're analyzing a waveguide and we're calculating all of the different modes. We would call two modes degenerate if they have the same propagation constant. They may look different, but in terms of the phase velocity, they will propagate with the same speed through the waveguide. So we'll call those degenerate. And if we have degenerate modes, they also very easily exchange energy. So we sort of expect here at this degenerate band edge that there's these different modes that suddenly propagate the same and they easily exchange energy, so that can enhance interaction with the structure even more, and thus the slow wave. So we finished our section on resonant structures that can give us slow waves, but I don't want to convey that I've touched on everything. I've just touched the tip of the iceberg, but hopefully showed you enough different examples that you get an idea of all the different things that can be done with structures around waveguides or other things to slow light down. The whole next big category, these are the pure materials. We're not structuring anything in this case, although I'm sure there's lots of hybrid configurations, but we're looking at a pure material, some very special material that introduces dispersion to slow waves down. In fact, the first time I had ever heard of a slow wave, I was sitting in on a talk of this new wonderful thing that I had never heard of before called a Bose-Einstein condensate. And essentially this is a very, very, very cooled material. And in this cooled material, it has dispersion, and we can shine light through it, and it will slow that wave down. There's also a phenomenon, it's kind of a touchy phenomenon, but it's called electromagnetically induced transparency. We remember from the Lorentz-Drude discussion at the beginning of the semester that around a resonance, the absorption spikes. It turns out through this electromagnetically induced transparency, we can produce in the middle of one of those resonances where it would have high absorption, we can suddenly reverse that, and the absorption jumps way down. And in the middle of what would be this high absorption, we get very, very low absorption. But what we end up having is all these material properties are jumping around. We have the most dispersion near a resonance, but suddenly this narrow window with low absorption. And it turns out in this window, we get the dispersion gives us our slow waves. We can also get slow wave propagation through something called coherent population oscillations. So here we're using something called a satural absorber. So imagine a material that's absorbing, and as we throw more and more light at it, suddenly it becomes saturated and no longer absorbs. So it becomes a little bit more transparent for high intensity. So it's a nonlinear phenomenon, and it turns out we excite this with a very strong pump beam, a signal beam, and we get a beat frequency. So it turns out the oscillations from that beat frequency, through some physics that I'm not really talking about, causes that material to have very strong dispersion, which then of course slows the light or the electromagnetic waves traveling through the medium. We can also slow light or electromagnetic waves by something called stimulated scattering. So this is two slides. On this first slide, I'm just introducing a concept called Brillouin scattering and a different one called Raman scattering. Very similar. So in a lattice, we can have sort of this slow bulk oscillation of atoms. So we heat something up, the lattice vibrates, and these sort of vibration waves, if you will, can travel through the lattice. And that interacts with the wave, and that it's a grating, so it can diffract light. Also, since it's moving, it can induce a Doppler shift onto the light. So light can scatter off these sort of slow oscillations of the lattice. That's called Brillouin scattering. A similar one is Raman scattering, and this is not a bulk oscillation in a lattice. These are the atoms shaking and vibrating so fast, but that can also scatter light. Now, in fact, there's two interesting things that can happen here. Not only slowing light, but inducing gain. So we'll take this magical material that has Brillouin scattering, Raman scattering. We excite it with a pump beam and a signal beam, and we get this beat frequency again. When that beat frequency matches whatever oscillation is in the lattice, that's when the magic happens. And in fact, when that happens, we can transfer energy from the pump beam to the signal beam, and that's called gain. And people actually make gain out of Brillouin and Raman scattering. But another interesting thing happen through this amplification process is that it induces dispersion. So the refractive index varies with respect to frequency, that's dispersion, and it also slows light. So that is it for not only slow waves, but this entire lecture series in 21st century electromagnetics. I hope you enjoyed it.